nowadays, several people cannot complete this work. That's my experience. Okay. Now, take a look on the existing network that we have. Let me expand that. Okay, now we have 27 students joining in the class. I don't know what happened for the rest of the student. Okay.
เพื่อนๆกำลังเข้ามาค่ะรอแป๊บนึงได้ไหม
ให้รอก่อนใช่ไหมครับโอเค5 นาทีอ่ะ
รอแป๊บนึงค่ะ
เคยออกข้อสอบนะต้องทำให้ถึงแถวๆเนี้ยนะฮะเพราะว่ามันจะมีการถามว่าโปรเจกต์ที่6+2หรือ5+2เป็นโปรเจกต์ที่น่าทำที่สุดอย่างเงี้ยนึกออกไหมครับนึกออกไหมโปรเจกต์ไหนเป็นโปรเจกต์ที่น่าทำที่สุดคือควรจะสร้าง e-exchanger กี่ตัวลักษณะแบบนั้นตัว delooping มันก็ต้องใช้ต้องใช้28 คนเดี๋ยวรอ 6.05 นะฮะอีก2 นาที
อาจารย์คะ for the project that you asked for this Friday like the group project for when you mentioned that you wanted in as soft file is it like as like what type I'm not
Well,
sure.
what I mean is you have to make the report but save in a soft file and then you send it like a PDF file to me. You don't have to print out.
Okay. So, but since you said that there's gonna be changes every week, will it be acceptable if like like how the way our group did, there might be some like errors and such maybe because it's like our first couple of times of using like Aspen.
Right. You can recorrect. You can correct it later. Because after I get it, after I get your report or the file, I will, you already and then ask you to do more. So you will add the information more and more to make the report, getting complete. You have to complete the final report again by changing or cutting off something that it is not important.
So it's just like when we're doing it weekly, so it's like to check our attendance and such, right?
Right. Not only attendance, because the topic that I asked you to do is quite important, right? So I want the group to emphasize and study more on that case, one for each. So you will learn about several things. Designing distillation column, just like what you learned in UK, right? So this is one case that you can work on distillation column, exchanger, reactor design, blah blah blah. But I will ask you to do only one example, not the whole process.
Okay, understood.
Okay. And of course, we're going to use the simulation to check your result, right? With the hand calculation and simulation. Of course, the simulation may give a bit different from your hand calculation, but that because of the properties. When the property change, the result will be, changing a lot.
Thank you.
Now, we now have 29 students coming. So can I continue to do the looping work? Now when we are talking about the loop, we actually what I have in the this is what I have before, right? So this is about the way of the pinch line. So we have hot utility 150, cold utility at 140. So I combine them together, They leave that line out, right? Consider about the first loop. The first loop is the heat will transfer to each other very well like that. So this is what my first loop is, right? This is what my first loop is. Do we have a second one? Do you have a second one? Yes, we do have another loop. Okay. So if I can move this heat exchanger, this is one heat exchanger, right? This is one heat exchanger. If I can move this heat exchanger to that one, so now I will reduce from 5 to, I will reduce from 6 plus 2 to be 5 plus 2 then. Then I have to move that, right? I have to move that. And combine this heat exchanger to that one. That's what I want. I want to move that heat exchanger to that one. So if I move, what happened to the heat load? What happened to the heat load? The heat load should be combined to each other, right? The heat load should be combined to each other. So it might become 140, but just keep it in mind. Alright? Now, let's consider about this one. If we have the assumption that the more that you move from the heat source to the sink, the more that you will have to have the, what's that, QHD and QC, right? So the more you move, the more you transfer the heat from one side to the other. It means you need to expand, you need to provide more utility on this side and the other side. The same thing. Now, if I move that to this one, being on what's that? The cooling hot speed, hot utility will be increased. Will not be equal to 60 anymore. Again, when that one increase, how much does the increase? Of course, the increase will heat. They will increase on the cool utility as well of 20. They should, because the work is parallel just like state function, right? So when that increase for this amount, they will increase for another same amount on the other side. Okay, now let me try to move that to this one and move that to this one. So what happened? Move that to to have this kind. So it is about the when I move, right, it's usually like this. I move this heat exchanger to that one. The temperature right here, you don't know right now. It used to have like 150 and 110, right? It used to have 150 and 110, yeah? This is 120. This is 110. 110 and 150 on the top. Right now you don't know. So just keep it. Then when I cannot change this one. I cannot change this one. Okay. Why difficult? Let's go. Now see, this is a previous word, right? I have 110 and 150. When I remove that out, temperature this one change, but temperature on this side cannot change. How come? See, temperature on this side cannot be changed because the temperature difference should be mean the point of delta T. Okay, should meet the point on delta T. This cannot increase to 126 degrees Celsius. It should fix on 110 because of delta T. We need to meet the delta T between these two strings, right? So I have to keep the temperature after remove that heat exchanger to still have 100. So what happened? You then going to increase the amount right there. Okay? You will increase the amount right there. So how can I know? I have to find out the temperature right there first. With the heat load of 40 kilowatts and the CP equal to 3. Can I get the temperature right here when the temperature right here is equal to 100? Yes. So the temperature right here equal to 40 divided by 3. 40 divided by 3 and then plus 100. So what I get there is equal to 113.3. See? 40 divided by 3 and plus 100, so you get 113.3. Okay? When you get 113.3, the minimum temperature on the top should be equal to 10 degrees Celsius different, right? So it's become 123.3. 123.3. At least. When you fix that temperature, now I fix the temperature right here, 123.3, right? Things have been changed on the heat amount that transfer from the top to the bottom, right? Because the temperature changed with about 83.3 degrees Celsius. 83.3 degrees Celsius. Okay, so Q on this case is about CP and multiply with 1.3, 123.3 minus 1. So the Q that can be transferred to this thing supposed to be equal to 166.67. no more 140 degrees Celsius, 140 kilowatt. Alright? So that will affect what? That will affect to this temperature. Used to transfer 140 degrees, 140 kilowatt. But now the amount changed to 166. So the temperature right here should not stand at 83 degrees Celsius anymore. So you have to calculate, right? You have to calculate. Of course, high heat transfer temperature should be higher than 83 degrees Celsius. So what it will be? So it is Q, right? Equal to 2.6, and temperature minus 30. So the temperature right there becomes 94.7. So I should swing that to 94.6, so 07 degrees. 94.07 degrees. No, it's 166.16 to 60. Right? So would it be effect to that heat load? Of course, because total, look at the total previously is 260, right? 260, right? Now, one have used more, 166, or 26.67 more, 26.67 higher. So what happened to that? You can do two things. One is subtract. So what you get is the heat load in this heat exchanger is only 113. This one effect to the top of forwards, right? So you have to calculate that one again, and that one will cause this one. Yes or no? Yes. Yeah. So that heat transfer amount will cause the temperature inlet or outlet, inlet. So the temperature inlet, instead of having 140 degrees Celsius, it becomes 113.4 equal to 4, right? 4. And T minus 10 minus 1 T. So it is temperature equal to, let's try 10. Is the temperature, what will be the temperature? 113.4 divided by 4, and plus 1, 0. So 138 and 138.3. 138.3. So that would cause what? The heat flow right there, because 138.3, right? Now you can calculate this, right? Or you don't need to. Do we need to calculate this? Yes. The temperature change and that amount change, and then you can when you have to do the balance, right? You have to do the balance. You have to do also the balance. The balance previously is 60 plus 60 plus 40 plus 80 plus 170. When the thing changed, the whole heat amount should be balanced at the same amount. Okay. So if I have that, if I fix that, I will go to add with that. Used to be 60 here, used to be 60. Now it's become 86.67 by 26.67 kilowatt more. So 26.67 more is will go to this side, because that side used to be 160 kilowatt, right? Now it's become 186.67 kilowatt. The reason that increase of utility is under this line. Under this line. What happened to this line is then like when you change temperature on each one and heat on each one, you change to the line. Actually, you have to practice by yourself. Take a look carefully which one affect to temperature and amount of heat will affect to temperature only. Right? Finally, what I can do, I will have 1, 2, 3, 4, 5 heat exchanger and 2 UTV. And then I can do what? I can do the slice and slice. Let me show you the slice. See, this is final that what I get. Okay. From this one, I can add for the annual cost index. As you can see that the pitch analysis, right? Even you are fixed now, you are fixed delta T equal to T. You still have some difficulty in finding how many heat exchanger that require in your process. Okay, so that's why using simulation is easier. Okay. Later on, I will teach in the class again about the heating. Okay. Now, the temperature that I can go is let's talk about the hot UTV then. Okay, the hot UTV that I can go is 250 degrees Celsius, right? Based on high pressure steam. Remember that? The high pressure steam can go up to only 250 degrees Celsius. So what happens if I would like to increase the temperature to 400, 500 degrees Celsius? Now let's talk about if I have high pressure here at 41 bar gauge, you will go to this degrees Celsius. And if you go for the 10 bar gauge of medium pressure steam, you will have the temperature will hit only to 184 degrees Celsius. And the medium low pressure steam of the full bar gauge, you can go up to only 160 degrees Celsius. So it's very difficult. Steam, very difficult to get to high temperature like that. So what I can do, I need to use natural gas or fuel oil and as an alternative to increase the temperature. So I get the table, and this must be 5.1. 5.1 show the composite of those fuels for heating value, right? We're talking about fuel oil. Light fuel oil, sulfur only 2.5. Heavy fuel oil 2.8. That will which one will you use? You cannot use just like what you want. You have to obey the regulation. You have to talk about the regulation. In this area, in the area of the Twin Towers, many people living in this area, so you cannot use high sulfur content. For the heating system, you have to use low heating content. Okay, low heating content of sulfur in that fuel oil. Okay. Of course, when you look at it, high heating content of sulfur in the fuel oil, you will have the heating value less, right? Less heating value. Okay, tell me about the heat and loss and net loss and net. The loss is mean when water coming out is leaving in vapor. Right? This is water in vapor. The net is the water is in liquid. However, if you compare with the natural gas, compare between fuel oil and natural gas. With natural gas, you will find a big amount comparing to 1 kilogram, like 1 kilogram. But this is 1 kilo, 1 kilo, big amount of natural gas. Right. Let's see in more detail. If you take a look on natural gas, of course, natural gas containing with the main composition of CO1, right? CO1. But in different areas, some areas may have CO1 in high amount, just like Salt Lake. But in Thailand, they have CO1 only 60%. And the main heating value is come from C1, C2, C3. That's it. In Thailand, we have the contamination of CO2
ฝนโทรศัพท์
25%,
โทรศัพท์
while the rest, I mean, other source in the world, natural gas contain very small amount of CO2 and sulfur, right? So it depends on. Now you're gonna, if you use the natural gas from Thailand, you may need a lot of natural gas to increase the temperature, right? Now if you look at the fuel oil, the fuel oil that silver grade, the high grade is grade E. That's why I'm talking about what? Light fuel oil grade E, light fuel oil grade. So sulfur content is only 1.67. But light fuel oil grade C, the sulfur content is very high. In Thailand, we may call like grade 1, grade 2, grade 3, something like that. Not A and B. So in the area of Pathum Thani, they allow to use light fuel oil grade 2, grade 2. So the sulfur content is only 1.8. Otherwise, the emission around here will be worse because we have high sulfur. Right? If someone to safety with me, you may be familiar with this kind of diagram, right? We use natural gas to burn, and what we want is to get the temperature on the stack. Okay? In safety, we want to know if we have fuel burning. We want to know what is the temperature at frame temperature. We want to get temperature of frame temperature. How can we calculate that? We use the standard state. Thermodynamic standard state to find out the temperature, the frame temperature, starting from standard state, right? Fuel oil with combust to get CO2 and water, and then we work with the hydrogen. Yes, this is hydrogen. Suppose that there is no heat. So the temperature right here can be calculated based on this equation. delta heat of combustion from that point will be equal to the summation of these three heats. Now, we go to this kind of equation, right? We know that if we have the methane burning with air, how much I can get? The heating value, the heat of combustion is around 802 megajoule per kilogram, right? So I use Cp as well to for oxygen, nitrogen, because we have air, right? And water and CO2. This will count into our calculation. Okay, let's see. Example R for the temperature outlet, the temperature at the flame temperature, right? We have natural gas, we have pure methane used in the furnace. Both fuel and combustion at 20 degrees Celsius. What I mean is fantastic. We want to know what is the flame temperature, but now we assume first calculate the flame temperature if methane is burned in, and just use that stoichiometric ratio of the dry air, right? So what I use is Cp. So Cp of oxygen at 200 degrees Celsius equal to. So what I get is around 200 degrees, 2,000 degrees. We have at 2,000 degrees Celsius, the oxygen Cp is 35.3, nitrogen 33.16, water 43.44, and 55.1. I stop working at this point. And delta heat of combustion is equal to 802.8 from the table as well, right? From the table as well. So I can calculate delta H. So I can plug that in Cp delta T equal to the heat. So what I can get is temperature. Flame temperature will be about how much? 18,000. Right? No, 2,076 degrees Celsius. This is very ideal. Right? Why? Because what we are concerned is the calculation have been done under dry air. Do we have dry air in the atmosphere? No way. Of course, you're gonna have like humidity 60%. Okay? If you have excess 50% of dry air, the temperature will be reduced to 1,800 degrees Celsius. When you have more humidity inside, the temperature will be reduced to 1,800 degrees Celsius. So, why do I need to understand about this flame temperature? Because later I can use with the pinch analysis together with TCC. What is TCC? Two composite curve. You remember what two composite curve? This curve. Oh no, GCC, grand composite curve. So what you get, remember that? You have this kind of graph, right? And this temperature, and this is H. So we're going to use that with the frame temperature. Now, I go to take a look at this. This is a kind of frame temperature. Okay. Now, of course, you're going to plot the frame temperature at the heat that you want. Okay, and then you draw two stack temperature, and then what do you get? You will get two region. One region is the one that you transpose. So we call that process E. The list of the region is about the heat loss. So what can I do with this? I can calculate the furnace efficiency, right? Heat to the process and heat to the process equal to 1 divided by heat released by the whole thing. So it is about 1 plus 2, right? So this is very common to calculate the furnace efficiency. Finding the temperature at the flame and temperature at the stack. And then just draw the line. However, you have to meet the pinch point. The pinch point will give you the less, if you hit the pinch point, your furnace will be highest. The efficiency will be high enough. The highest. You cannot go higher than that. Alright? Okay, now let's see. If I have, see, this is the grand composite curve, right? So this is our grand composite curve. The red side is our grand composite curve. The frame temperature is right here. After I calculate, right? I have to draw to that point. So this is telling us about stack temperature. The stack temperature probably at the pinch temperature, the same one. Okay? If you have high frame temperature, draw passing to the pinch line, pinch point or stack temperature, you will get number 2, right? Stack loss. And number 1, okay. Right. So the efficiency of that furnace, the red furnace, is equal to 1 divided by 2 plus 1. Now let's see. If I cannot increase, my air, my natural gas cannot burn and get the temperature high enough, like the red one. I have the green one. I can increase the temperature to only this to that point. So I draw the line. See? So a lot of more stack loss will occur when you have low frame temperature. We have low frame temperature. You're going to get more heat loss on this. Therefore, the efficiency is still equal to 1 divided by 1 plus 3. This is 3. So the conclusion is the lower stack temperature, the higher. So mistake. The lower stack temperature, the lower furnace efficiency. condensation occur. Otherwise, it will not good to the people living around the furnace and around the factory. Okay, so that's why you cannot, if your natural gas, if your fuel oil contain a lot of sulfur, you must thinking about the acid dew point. So what does it mean? Your acid dew point, it means sulfur like that. You condense when the temperature below 150, 160 degrees Celsius. So you cannot have the set point lower than 160 degrees Celsius. Even though the pinch point equal 1 to 10. Even though the pinch point equal 1 to 10, if you have sulfur contained in the fuel oil, you have to pass to 160 degrees Celsius, not 120 degrees Celsius. Alright? Let's take a look at this. Now, even though I have the pinch point equal to 120 degrees Celsius, flame temperature cannot pass to the pinch point. You have to pass to the dew point, at 160 degrees Celsius, to prevent acid gas condensation, right? To prevent acid gas condensation. So now you can calculate the efficiency, right? Efficiency of the furnace. How about if I have the grand composite curve like this? This is my grand composite curve, right? That's different because the transfer heat moving is coming close. So now you cannot hit to this point or even this point. You have to hit to the point of that grand composite. If my grand composite curve is right here, so the drawing line drawn between the flame temperature must pass to the effect, the turn of this grand composite curve. So it must be doesn't matter on the dew point or the pinch. The draw to pinch point, it gives you 1. When everything passes to the pinch point, it means everything good, high efficiency, right? Everything good and high efficiency. But in the real world, we have to concern about the fuel characteristics. Higher sulfur, you cannot go to the pinch point. You have to go beyond the dew point of the gas, acid gas. Or you have to rely on the grand composite curve as well. Okay? And now, let's take a look on example 5 that flow pilot flow. Pilot flow, right? Now, if I already calculate that, my system has the combustion because of temperature that I want may be higher than 250 degrees Celsius, right? I need to use the natural gas or fuel oil to burn. After I calculate, I found that the flame temperature equal to 800 degrees Celsius. And there are some sulfur content, some sulfur content in that view. So we have to consider about acid dew point, right? And the acid dew point is 160 degrees Celsius, like that. Our pinch analysis, delta T mean equal to T. While the delta T mean between fuel or pure gas and heating system process heating for the heat transfer is about 30 degrees Celsius. So tell us about how much fuel required and the efficiency. The fuel required, just like what we want, right? We want how much that we want to burn that and get 1800 degrees Celsius. Okay? So there are two. The solution is about delta T 30 degrees Celsius. The 30 degrees Celsius, you need a gap, right? Delta T is about the gap between frame and the process at pinch. The process at pinch, you reduce about half of that. So delta T between fuel and process is 30 degrees Celsius. Half of the delta T is 5. So the point, because we have delta T, the point of frame temperature will be not equal to 180 anymore. It's become 1775. So I mark 175 in the point. Where should I mark? It's about 7.5, right? Remember, we have 7.5. It's 7.5. This is what? The grand composite curve. This is the grand composite curve, right? This is our grand composite. But, of course, the line is very difficult to see. This is on our example 1. Then we have 7.5 right there. So 7.5, 1775 is coming from the delta T, right? And now, you can draw. Now you can draw from the frame temperature down to this diagonal lines here. If you take a look, one below is at pinch point. Pinch point is 150 degrees Celsius, right? 145 degrees Celsius. But because of dew point is 160 degrees Celsius. Okay? 160 degrees Celsius. So how can I can draw the first line at the pinch point, and the second line to pass to the dew point. Let's come to this one, right? Right? So this graph will tell you about what? How much? You need fuel equal to 7.5, right? 7.5 plus this is 1. So it is about 6 plus 0.6, then 8.3 megawatt. 8.3 megawatt. I'm going to remember 8.3 megawatt. Okay. If I use natural gas, this means I divided by the heating value. Heating value is equal to 55 megajoule per gram. This is for natural gas. So it means how much I need the natural gas? 530 kilograms per The grand composite curve can tell us about how much the heat that you lost during the step and inside. See? So this is amount of fluid or fluid gas that need to apply to the system. How about the efficiency? Can you find out for efficiency? Yes. I can find out for the efficiency, right? Which is equal to 7.5, right? Divided by 8.2. So it is will it be good to this furnace? Yes. It's become 9%. This is different from any heat exchanger. Other heat exchanger, they don't have efficiency getting high to 90%, mostly 70, 80%. But furnace, this is a case of furnace. We use furnace when we want to increase the temperature to very high, more than 300 degrees Celsius. So it is very a must case for any refinery to cut money. You don't cut furnace. So we need a pinch line, a grand composite curve, a T composite curve, two composite curve to calculate with the efficiency as well and amount of the fuel oil that used. Okay. Now the last topic that we need to learn is one. The last topic. That we need to learn is next page. This is the last topic. Now, people may ask about how many pinch that I can have. You can have one pinch. You can have multi pinch. Point, right? Or you can face this kind of threshold. You can face the problem of threshold problem. There is no pinch. Right? When you have no pinch, what does it mean? Okay, let's try. Right? I have this kind of flow. Too hot, one cold. Too hot, one cold. Seem like we can transfer, right? We can transfer 250 and 205. Can it be transferred or neutralized the heat? So I try. Let's make the delta T equal to T. Okay? When the delta T equal to 10, this is you can try in the Excel file that I get. I found that put delta T equal to 10, QH mean you have no QH mean, but QC mean 46. I increase again. When you need the problem of threshold problem, you just increase the delta T from 10 to 60, then you will get QH mean equal to 0 and 46. What happened? When I increase that to 10.5 degrees Celsius, 105 degrees Celsius, I start to have QH and QC 52. So now I can plot back. Delta T need to be increased. Otherwise, we won't see hot and cold mutually. So what does it mean? In this case, we we do not recommend because the delta T means different like 105 degrees Celsius. What does it mean? It means your heat conservation, the heat conservation inside the process. Right? You need to have the delta T small as much we can, but not this high temperature. So what does it mean? Even you can have the QH mean and QC mean, it doesn't work to do the pinch. It doesn't work to do the pinch. Right? But it is kind of like 20 degree, 30 degree different in T is unique. So in this case, if delta T equal in a large amount, you will have no problem on capital points, right? But in GD, you will have a problem on capital points, but not very much on the GD. Okay? So however, if the delta T is less than threshold, your GD may not affect much. But when the delta T is higher than the threshold, it will affect much more. So first, when you have the problem on several string, you have to check first whether you can get delta T that provide your site. Okay? So check with the Excel first to have this tree with the small value of delta T. นะครับก็ทำไปต่อครับผมทวนอีกครั้งนะสรุปก็คือว่าตอนเนี้ยเราได้โจทย์อะไรมาใช่ไหมassume ว่าเราได้โจทย์ข้อนี้มาอะไรนะเปิดท้ายก่อนสิครับได้สามได้เปิดท้ายก่อนได้สามได้เปิดท้ายก่อนเห็นท้ายบทไหมเห็นท้ายบทไหมครับมาให้ดูนะ นี้ใช่ไหมคุณไม่โทษทีคุณไม่แชร์แชร์Okay, suppose you got this kind of problem since this is midterm years ago. So when you get this kind of problem, what you have to do is find out the delta T first, whether it is can be applied to the pitch or not. Okay, but in this case, I only assign delta T equal to 20, right? And then you must do what? The heat exchanger network. After the heat exchanger network, you have to draw this network, redraw the network again. And the network changing from that one, right? Not complicated one, to the complicated one. See that? This is one kind of problem. Okay, let's take a look on another midterm. Another midterm exam. I think this one. This one. This is very easy one. 2 years ago. So I have the diagram, and then ask you to redo the work by using delta T equal to 20 as well. Right? Not difficult. Look at another year. This is 3 years ago. So now I ask you to find out the pinch hot, pinch cold, right? HU hot utility, cold utility. แล้วก็ไงฮะ you have to make the network heat exchanger network, right? After you make a heat exchanger network, you have to dilute. I don't know what it is. Dilute and then find out which heat exchanger match to the one that I gave. Okay, and then calculate the rate of it under the cost analysis as well. And calculate ลองคำนวณซิว่าที่ rate of it เนี่ยมันน่าทำไหมจากการตกลงบอกว่าถ้าเราจะเลือกที่ rate of it ก็ต่อเมื่อการลงทุนไม่เกิน6 million บาทถ้าเกินไม่วันนั้นต้องตอบได้ว่าจะลงทุนหรือไม่ลงทุนเข้าใจไหมครับเพราะฉะนั้นก็จะโยนมาถึงตัวไหนถึงโจทย์ข้อนี้โจทย์ตัวอย่างนี้ในโจทย์กันบ้านนี้โจทย์มิดเทอมนี้ไม่ถึงที่ไหนไม่ถึงตัวความร้อนจากฝุ่นนะจะแค่การเลือกกำหนดของเยชินเจอร์ส่วนใหญ่แต่ขอให้รู้ไว้ว่าในกรณีที่มีความร้อนจากฝุ่นก็สามารถทำได้เช่นกันเห็นไหมครับอาจจะติดๆขัดบ้างนั่นจริงอยากสอนในห้องมากกว่าเพราะว่าพาร์ทนี้ยากพาร์ทนี้เนี่ยยากที่สุดครับเดี๋ยวอาจจะมีการไปสอนในห้องอีกนิดนึงนะครับอดใจนิดนึงก่อนนะก็คือว่าตอนนี้ให้เข้าใจ whole concept ก่อนว่าเราต้องการแล้วเดี๋ยวผมจะไปรีวิวติ้งในห้องนะครับเห็นไหมตอนนี้อาจจะผมไม่รู้จะเขียนยังไงให้คุณเข้าใจต้องค่อยๆทำไปพร้อมๆกัน Any question? That's it for today. And I think pinch analysis will be in the midterm exam. But I think I heard that the midterm exam will have a short period, like 1.5 hours instead of 2 hours. เขาจะลดเวลาลงเรียน1 ชั่วโมงครึ่งซึ่งมันจะออกข้อสอบยังไงไม่รู้ก็เลยคิดว่าอาจจะมีการนอกรอบใช่ไหมนอกรอบตัวพินช์ไปเพราะว่ามันใช้เวลานานในแล้วก็อย่างที่โจทย์ข้อสุดท้ายนี้น่าสนใจมากเพราะว่าใช้เวลา3 ชั่วโมงเป๊ะเลยในการทำสำหรับนักศึกษาเนาะลองทำมานะถ้ามีอะไรก็ลองมาทำดู Any questions?
I do have a question.
Yes.
It's about the part where you were drawing the GCC, the big graph.
Okay.
Page
number 128.
Yes.
Okay.
Yes. I'm just wondering, like the part where you said that the temperature, the T dew point, the acid dew point is 160, and then you also drew an arrow saying that it's also 145.
See, this the blue dot. Look at the blue dots. Can you see the blue dot here?
Yes.
Yeah, this is about our GCC. This is our GCC. Right? So the blue line. The blue line. I draw that to hit the pinch point. Okay, 145 degrees Celsius. The grand composite curve, that one, come from what? Come from which one? Come from this one. 145. I use this one. I use this data to plot that one.
So like the graph were like compressed, I think, right? Yeah, it's compressed, so the dots are like really close together, but they are not at the same point, right?
At the same point, this is the maximum is going to 240 degrees Celsius, 250 degrees Celsius.
I meant 160 and 145.
145 is for our pinch point. 145 my pinch point. But in this case, our fuel contains some sulfur, right? Contains some sulfur. So I need to concern about acid dew point. 160 degrees Celsius. So I have to draw that one. This is, I just want to show you. If your fuel contains some sulfur, you cannot use or answer. You cannot answer on the blue line. You have to answer on the red line. Okay, because the red line is 160 degrees Celsius. But it's very difficult to draw different. Or I have to leave the red dot over here. So the red line represent the flame temperature passing to dew point. The blue line inside below, little bit below, right, represent our own calculation. You don't get, right?
No, I get it. Yes, I saw the two lines. Yes.
Okay. There's two lines here. One is without concerning of the sulfur content. The red one, when you have sulfur content in your fuel. So of course, you can calculate differently. But what I did is only on the red line. On the blue line, a little bit different, right? You may have on the pinch point, you may have 91%. Dew point, when you consider about dew point, you get 90%, something like that.
Okay, yeah. Understood, yeah.
Thank you. No problem. Any more questions? Actually, if you have this book, which is written by the professor. Okay, let's go. You have this book.
Yes.
You got this book, right? It is in what's it then? That's it. Now, chapter 3. Relation journey 126, right? 126. I think about it, it's not very complicated. Very easy. I also use this on Tuesday. It's fine. You can also look at this. In case the above pinch and below pinch, they cannot combine to each other based on the CP hot and CP cold, which one greater or lower. You can do by split line. Split line. See? You can do by split line. Because we try to after split line from 60 it's become like from 60 here maybe 20, 40. You have to assign on it to make sure that you can link between another skin นึกภาพไหมครับนึกภาพไหมครับ any question on that โอเคเอาใหม่นะว่าดู Suppose I have okay, let's take a look on this. You will take a look on this. This is below pinch. The hot one should be higher than cold one, right? The hot one should be higher than cold one. That's why this is 0.25, 0.15, 0.2. So only one will possible. Only one possibility here between H1 and C1. So how can I make this link? I can make this link by split the line. You know this? I can split the line. 0.15, then I split the line to 0.1. All of this become 0.2 unit. So now CP hot higher than CP cold. So we can just boom and boom. You guys should take a look on that because I didn't mention that because I think you must know about the split line, right? The split line. So in this case, higher than that one, so very easy to try. ก็เป็นเทคนิคตัวหนึ่งนะในการที่จะทำให้ตัวมันเป็นไปตามเลยนะ requirement ของตัว constraint เนาะany more question เดี๋ยวจะไปดีลูปในห้องอีกครั้งนึงไม่งั้นเดี๋ยวคุณตามไม่ทันมันยากเห็นไหม Okay if there is no more question can I leave the room now ไม่มีคำถามแล้วนะครับเพราะฉะนั้นพรุ่งนี้ภาคไทยเจอกี่โมงนะเที่ยงครึ่งนะครับห้องคอมนะถ้าไปเร็วได้ก็รีบไปเปิดคอมก่อนขอบคุณมากครับแล้วคุณนายในวัน